In this video, I will discuss the mechanical energy balance. I'll start the discussion by quickly reviewing the open system energy balance. Q plus shaft work is equal to the change in kinetic, potential, and enthalpy. Oftentimes in chemical engineering, we say that the change in enthalpy is much, much greater than a change in potential energy or kinetic energy, and therefore these terms are oftentimes canceled. However, in other processes in chemical engineering, you can't necessarily neglect these, especially if there is not a change in enthalpy. So just to review, enthalpy is a function of temperature, pressure, phase of matter, and also chemical identity. And if none of those things are changing, then you wouldn't expect there to be an appreciable change in delta H. So an example of a type of process that you'd not expect to have a change in enthalpy would be simply fluid flowing through a pipe. And this is oftentimes where you see the application of the mechanical energy balance. So for simple liquid flowing through a pipe, there's not going to be a temperature change. There's also probably not going to be a phase change or a reaction, so the chemical identity will not change. There may be a change in pressure. However, as I've noted before from looking at the steam tables, the enthalpy of a liquid is not a strong function of pressure. It's more of a weak function of pressure. So therefore, for an application like this, where I don't have a delta H, in this case, changes in kinetic and potential energy may become more important. So that's the rationale for why we'd want to derive the mechanical energy balance. Okay, so next let's take a look at the derivation. So I'm going to start with the open system energy balance as described above, and I will make substitutions to that based on the derivation procedure. So it's delta H dot plus delta EK dot plus delta EP dot is equal to Q plus shaft work. And if you remember in a previous video, I defined the thermodynamic quantity of enthalpy to be equal to U plus PV. So H is equal to U plus PV. This is something that you'll talk more about in your thermodynamics and your phase courses. So I can rewrite this because kinetic energy, potential energy, and enthalpy are all going to have a mass flow rate in them. I can pull out a mass flow rate. So if I factor out the mass flow rate from this, all my extensive variables are going to become intensive. So my delta H would become delta U hat plus delta P V hat. Put that in parentheses. Plus, remember the kinetic energy is 1/2 mu squared. And if I factored out the m, it's going to be delta U squared over 2. And potential energy is mgh. So if I factor out the m, I'll be left with the g, and the delta part comes in with the change in height. So that's the left-hand side. I'll keep the right-hand side as Q plus shaft work for now. I'm going to make a couple other steps. So instead of specific volume, I can write that specific volume as the reciprocal of the density. And I can also, in this step, divide through by m dot. So let's make those two simplifications. This is the result from doing those operations. I've also brought the Q over to the other side, Q dot divided by m. The next step is I'm going to define the frictional loss to be F hat. This is frictional loss, and I will define it to be equal to the change in specific enthalpy minus Q over m. Frictional loss, and this is equal to delta U hat minus Q dot over m dot. So if I rewrite it in that way, I can obtain the final form of the mechanical energy balance, delta P over rho plus delta U squared over 2 plus G delta Z plus F hat is equal to Ws over m. This is what we call the mechanical energy balance, and this is good for situations where kinetic and potential energy changes are expected to be non-negligible. Now we can take this mechanical energy balance a step further if we make a couple of other assumptions. So if we assume that there is no friction in the flow, frictionless flow without shaft work, we will obtain a familiar expression from your physics course, the Bernoulli's equation. And that is delta P over rho plus delta U squared over 2 plus G delta Z is equal to 0. Once again, this is called the Bernoulli's equation. And this is good for flowing fluids, so good for drainage or siphoning from a container, as well as some other applications, which I'll show in the next few videos with some example problems. That will conclude this video.